Welcome back to class 22. Here's Borgnacki's example 6.7. In a reversible process, nitrogen is compressed in a cylinder from 100 kilopascals and 20 degrees Celsius to 500 kilopascals. During the compression process, the relation between the pressure and the volume is PV raised to the 1.3 equals a constant. Therefore, this is polytropic and the N exponent is equal to 1.3. Calculate the work and heat transfer per kilogram and show this on a PV and TS diagram. And you know, I put this in here. This is actually a spoiler alert, right? That's the spoiler of what we're looking to do, right? So they've actually given you the solution there. So even if it's not 100% necessary, I like to draw. I think I can just stop saying that right there. Yeah, I like to draw. Trying to think of and picture this thing. We got this. And it's compressed, right? So we're compressing this. So I think we're putting work into the thing and going from one state to another. Yeah, so we're going to work in. And know it's a polytropic process. So we know we're going to go from 1 to 2 with a P2V2 minus P1V1 over 1 minus N. From the stuff that we just did a moment ago, right? So what we want to do here, we actually have a couple choices. I'll show you that we could have done something else, right? We also have the choice of going R times T2 minus T1 over 1 minus N. And you might ask, where's the M? Well, I should have made this a lowercase w right here, because they didn't tell us anything about the amount of mass, and they didn't tell us what the volume was, so we can't find the mass. So we're going to do this on a per mass basis, so that should have been lowercase, and these are lowercase, so there's no M right there. So this would have been the fastest way to do it. Is that true? No, it's not. Okay, so now we don't know the temperature right here. So we have either two choices. We don't know we don't know the volumes. Okay, so we had to find one of these things. We know neither one of these specific volumes. We don't know this temperature, but we know we could find the rest of the stuff. So that's our approach right here. Write down that equation and kind of see, well, what do we need to know to be able to use it? First thing we know is we're going to have to get some things from the book. So this is nitrogen, and we're not used to that. So let's write everything we have down from that off of table A5. So we have nitrogen, and so here are the things that work out for nitrogen. You can see that it's pretty darn close to air, right, which is up here. It's got the same K. Right? We don't need K because this is for isentropic processes. We have a polytropic process, and we note that we are our polytropic coefficient exponent, is smaller than that K, right? This is 1.4 here for this thing that we're looking at. I'm going to write, like I said, I'm going to write all of these down for this in case I need it, but I might only need a couple of them, and that's going to be 0.2968. I won't write down what the units are this time, just for speed, but usually it's good practice to write what they are, part of the thinking process, and then I'll write them. Okay, so just makes for exciting things here. So anyway, you know what? Good practice. It is a good thing to do, to write down what the units are. You're thinking your way through the thing. You haven't turned your brain off. You're not simply plugging and chugging. You were actually thinking. And that was supposed to be 1.4, but it didn't quite come out. All right, so my approach, we had two choices, really. It might have been the simpler choice to just go ahead and find T2 because we were given T1. So one thing I also didn't do that I usually do is I'll write what T1 is equal to 20 degrees Celsius or 293 degrees K. P1 is 100 kPa, and P2 is 500 kPa. The fact of watching that out, writing that down can sometimes help me and my thinking my way through the problem. We also noticed n is equal to 1.3. Okay, so these are like the givens, and I should have written the givens. Here's the lookups. We did the lookups. Here's the equations that are kind of like at the heart of the first thing we want to do, and it helped us recognize the next thing I want to do is either find T2, because we don't know m here, but we do have T1, we do know n, we just looked up r, we'd be able to find work. The other, alternatively, we could find V1, and then we could find V2. Well, I chose, because I didn't cheat and look up and see what the solution was, I went ahead and did V1. So I'm going to stick with that. V1 we can find from the ideal gas law. So PV is equal to RT over P. And we were given these two things, and we know that. So go 0.2968. And T, make sure we put it into absolute, 293, and divide by 100. And we will find that we have 0.8696 cubic meters per kilogram. And now we'll use our polytropic to find the other V1, right? So the polytropic equation is the V1 over V2. Double checking here, we always have that 2 over 1 and 1 over 2 when it comes to the pressure and the volumes of the thing. So we could rewrite that thing out. So V2 is equal to V1 times P1 over P2. I believe I got that right. And that's the 1 over N, right? So just some flipping around and manipulation of the thing. And so we got 0.8696, that should be an equal, not a minus, times 100 over 500. Raised to the 1 over 1.3. And we're going to probably expect a smaller value, and sure enough, but we've compressed it, so that makes sense that the volume is going to be less. All right, so now we can go ahead and put this back up in the top, 1 to 2. So the pressure is 2 is 500. This is pressure, volume 2 is 0.2522, minus P1 is 100, and V1 is 0.8696. And here's something to keep track of. 1 minus 1.3. That's going to tend to be, that's a negative number on the denominator. And depending on what the proportions of these two things are, I mean, these together could be larger than that, and that would make it a positive, but it turns out that they don't, right? That this is bigger than that. So the numerator is positive, but the denominator is negative. So notice that you get negative 130.4 kilojoules per kilogram. The alternate approach that you could have taken, and what's written down in the book, is we had T1, P1, and P2, so we could have, instead of using this equation right there, right? So the maybe we do want to know what the second temperature is, so we will write that here, right? So we would use this, and we're going to P2 over P1 raised to the n minus 1 over n. So we can find T2 by taking T1, which is 293, and multiplying it by 500 over 100, which is raised to the 1.3 minus 1 over 1.3. So we end up getting 424.8 degrees Kelvin. And I like to just see what that is for my own benefit, to kind of get my head wrapped around it. I get a better idea what 100 degrees Celsius is where water boils. I know that as a reference point, so we could see it. Oh, it's 150. Makes more sense. I don't have that in my back pocket when it comes to Kelvin. So we, alternatively to what we had done right in this section right here, we could have gone to this right away and then gone up to this equation And if we did everything right, it should come out to that same value right there. Okay, so but it's a good thing to know what the end state temperature was anyway. It's good to know all of this information. So that we do have, this is one of the things we asked. We asked for the work per kilogram, and now we want to get the heat transfer. So when we're doing that, we're almost always going to want to look at the conservation of energy, which is going to be it should be lowercase. All right, that's fine. Lowercase is good on this. Remember, this is a chunk, so we can use this one with the internal energy. Q1 to 2 minus work 1 to 2, all of them per mass. We have a choice, actually, when it comes to these. We have an alternative approach if we would like to do it. But I'm going to go ahead, as we mentioned in the last class, we haven't assumed constant specific heat yet. This is for an ideal gas, but in terms of the equations that we've used, we have not established that it has to be constant specific heat. But we get down to this point right here, we have a choice. We can use constant specific heat, which is going to be like, delta U is going to be CV delta T, right? And that assumes constant specific heat. Or we can look up this U in this table right here. A7, A71, yeah, right here. So we have the two temperatures. We have it at, in between there, right? Because we're 293. We could look up what the U is in this, and then we also have the 424. So we could find out in between here. We could find out what these two U's are and use that in here, or we could use the CV. Let's go with the CV. So we're solving for here. So we're going to go Q 1 to 2 is going to be equal to U2 minus U1, or CV T2 minus T1, and plus W1 to 2. But remember the sign conventions, right? This is negative because this is work in. Right, I should have said that when we got that negative. What does that negative mean? That means we're putting work into. We're going, jumping ahead to the graph. We're going from 1 and we're going that away right here, and we're making this volume smaller. We're compressing. So in order to compress, we put work in. If we're expanding out, we get work out, which is typically what you do with a piston engine, right? As the piston expands, that's when you're collecting energy and turning a shaft. So, we're going to go ahead and put this in. We wrote this as positive because that's what the equation's for. But when we're going to put a negative value into there. So we say CV, which we got from right here, 0.754. 745. He said the number backwards as usual. T2 is, well, you can use Celsius too if you want to, but it doesn't. As long as it's because it's just a difference, right? As long as you use both of them as Celsius. Here's your 293, and then we're going to go plus, but then we're going to minus 130.4. And we end up with a negative 32.21. What does that mean? Well, that means, the typical one here, we are going to, when it's positive, we're putting heat into the system, right? So therefore, if it's negative here, that means we're taking heat away, right? So we're putting work in and we're taking heat out is what those signs mean, right? I did it with a big Q, but it's supposed to be a little q. So here's right here. So there is the two things they were asking for, the work in and the heat out. You could also, we want to take a look at a little bit of these graphs right here. So this one's pretty good, right? We're following, you'll recall what we're doing here. This is the important part where we're starting to kind of use this knowledge right here, right? We could say perhaps that because our 1.3 is lower than the 1.4 of the gas, we are actually kind of coming, yeah, when n is, yes, okay. So like we're in between, right? So here would be, I think I'm going to say this the right way. Yes, all right. So here's the isentropic way, and we are above the isentropic curvature. Right? We still have a curvature going on to it, but it's not the same curvature as the isentropic one. An isentropic would have been straight up and down, right up here, right? From we're going to 1 to 2. We're coming in this direction, and once again, okay, yeah, because n is less than k, right? So that's what that curvature means, where we're coming and we're making that path. And we know the temperature does go up, right? So that also tells her. So that's like informing us on how to graph this thing without actually having the values in front of us. Although we don't have the S, we didn't calculate the entropy in front of us. But we could have, I don't think any, with the, if we continue on, with the, if we continue on with the assumption of being constant specific heat, recall that we could go delta S is going to be equal to Cp natural log of T2 T1 minus R ln P2 over P1. Okay, and I don't think this is, I don't think it's required that this is any type of process, although I kind of think it should be. Honestly, I kind of think it should be, because I think in order to write this, you may, I'm actually have to think about that some more. One thing left to do when it comes to that right there is note that on our cheat sheet, this was a polytropic process, and here's what we had for that one. And you'll note that we had n minus k as part of that. So that's an interesting one in there. So I want to talk some more to Dr. Yevisterk about how to go to this, because that still remains a question for me as to, I'm not sure how to get to this. I might go back to the source material and see if there's anything before this, because I just collected all of these like years ago. I made this cheat sheet. And I want to see if there's anything before this to put this into context, into what the assumptions were that came into there. Because I actually plugged the values of directly into here, and I got a slightly different answer, right? So I'll just show that unless I'm writing it down. I plugged them in, and I got a negative 0.09064. And then if I plugged into the one in the cheat sheet, I got a 0.09224. All right, so slightly different. So, but this is more of interesting. They didn't ask that in the problem. We'll see in the next video with more examples. These are going to be not the examples out of the book. And Sengel started to depart from their from the order of topics. In their chapter 7 is different from the chapter 6, so I'm not really going to stick with the Sengel examples as my backup. I just picked some more problems out of Bornacki, and hopefully those will be useful and helpful to you. See you soon.